Mabuhay and magandang Jansan. This is Fernan Tabsing, and today we will be discussing the linear programming, the graphical method. What is linear programming? Linear programming is a mathematical technique used to find the best outcome, like maximizing profit and minimizing cost. Linear programming widely used in business, economics, engineering, and other operational research for decision making. And what are the key components of linear programming? Linear programming has three components. First, objective function. Second, constraints. Third, non-negative constraints. When we say objective function, the formula you want to maximize or minimize, like for example, the profit or cost. And when we say constraints, the limitation or condition the solution must meet, like for example, resource availability. And for the non-negative constraints, variable must be often non-negative, like for example, you cannot produce a negative number of items. Graphical method. It is a visual approach to solve linear programming problems with two decision variables. And why we use it? It is simple and provides a clear understanding of how constraints interact. And now, let's have a presentation coming from YouTube channel of Joshua Manuel about linear programming maximization. This video explains the components of a linear programming model and shows how to solve a basic linear programming problem using graphical method.
Welcome to the first video in this linear programming series. In this video, we will graphically solve a basic maximization linear programming problem using the extreme or corner point approach. What we have here is a linear programming or LP model. The X and Y in this model are referred to as decision variables. They tell us what quantity to buy, produce, sell, or transport, and so on. The 2x plus 5y here is referred to as the objective function, which we want to maximize. In linear programming, we either maximize or minimize the objective. The next two lines are called constraints. They are restrictions that shape how you attain the objective. Let's call them C1 and C2 for reference purposes. Since we're dealing with real-life objects, we do not expect them to have negative values. So the last line here tells us that both x and y have to be greater or equal to 0. We call them the non-negativity constraints. To solve the model graphically, we begin by finding points that satisfy the constraint lines. For the first constraint, when x equals 0, y equals 8. And when y equals 0, x equals 16. For the second constraint, when x equals 0, y equals 15. And when y equals 0, x equals 9. Now, when drawing the graph, we usually just stay in the first quadrant here, where both x and y are positive because of the non-negativity constraints. So for the first constraint, we have the points 0, 8 and 16, 0. We join those 2 points for the constraint line. We do the same for constraint 2, 0, 15 and 9, 0, and then draw the constraint line. Since these constraints are less than or equal to constraints, they will be satisfied in the region below the lines towards the origin. Therefore, the region satisfying both constraints simultaneously is this one here. It is called the feasible region. That is, any point in this region is a feasible solution. In particular, the optimal or best solution will occur at an extreme point or corner point of the feasible region. These are the corner points for the feasible region. Let's label them 1 to 4. The optimal solution to this linear programming problem will occur in at least one of them. To decide which one is optimal, we will find the coordinates of the point, plug them into the objective function, and then choose the best. At corner point 1, the coordinates are clearly 0, 0. At point 2, 0, 8. At point 4, 9, 0. Now, those are easy to see. For corner point 3, we can see that the coordinates are 6 and 5 by eyeballing, that is, looking at it very closely. But eyeballing is not usually the best way to go when finding the intersection of two lines, especially when manually drawing the graph. So let's see a way to solve the two equations simultaneously to determine the actual coordinates. Here are the lines for the two constraints. Now suppose I choose to eliminate x. Note that the coefficient of x here in C2 is 5. Then I can simply multiply the first equation by 5 to give 5x plus 10y equals 80. And then we can subtract C2 from the new equation. So 5x cancels 5x, 10y minus 3y is 7y, and 80 minus 45 gives 35. And on dividing both sides by 7, we have y equals 5. To now find x, we substitute y equals 5 into any of these three equations. Suppose we choose C1. Then we have x plus 2 times 5 equals 16. That is, x plus 10 equals 16, x equals 16 minus 10, and x equals 6. So the xy coordinates for extreme point 3 are indeed 6 and 5. Next, we determine the optimal solution point by finding the corner point that gives the best value of the objective function. The objective function was to maximize 2x plus 5y. As you can see here, the objective function, or its value, is sometimes represented with z. So now, the xy coordinates at point 1 are 0, 0, and substituting that in the objective function gives 2 times 0 plus 5 times 0, which equals 0. And at point 2, we have 0, 8. So the objective function value is 2 times 0 plus 5 times 8, which equals 40. The coordinates at point 3 are 6 and 5. So z equals 2 times 6 plus 5 times 5, which equals 37. And finally, at point 4 with 9, 0, z equals 2 times 9 plus 5 times 0, which gives 18. So here we have it. Point 2 provides the highest value of the objective function. So the optimal solution occurs at point 2, and it is x equals 0 and y equals 8. And the corresponding objective function value is 40. And that concludes the solution to this LP problem. Thanks for watching.
Another video presentation from the same reference about linear programming graphical solution minimization problem. And this video shows how to solve a minimization linear programming model graphically using objective function line method.
Welcome. In this tutorial, we will graphically solve this minimization problem using the objective function line approach. Note that the use of the graphical approach is limited to two decision variables. We start by finding points for the constraint lines. Let's label them C1 to C3 for reference purposes. For constraint 1, when x equals 0, y equals 2. And when y equals 0, x equals 6. For constraint 2, when x equals 0, y equals 5. And when y equals 0, x equals 2. For constraint 3, y is just always less than or equal to 4, irrespective of the value of x. In drawing the graph, note here that the highest value of x is 6 and the highest value of y is 5. And that is what tells us how far we need to go on the x and y axis. You can see that I went a little bit higher than 6 on the x-axis and a little bit more than 5 in the y-axis because I have the space. So drawing the line for the first constraint, we have the points 0, 2, and 6, 0, which we join to form the constraint line. For the second constraint, we have 0, 5, and 2, 0, which we also join to form the constraint line. For y less than or equal to 4, the line is simply at y equals 4. Now, since the first two constraints are greater than constraints, they will be satisfied in the region above the lines away from the origin, and y less than or equal to 4 is simply satisfied below the line. The direction of the arrows show that the region satisfying all the constraints at the same time, called the feasible region, is this area shaded in blue. Now, the optimal solution to this problem will occur at an extreme or corner point of this feasible region. Let's label them A, B, and C for reference purposes. Now, recall that the objective function is to minimize 5x plus 7y. So the corner points that gives us the minimum value of the objective function is the optimal point. Instead of testing every single point, we will use the objective function line approach. We begin by setting the objective function to any number of our choice. To make the process easy, we can simply multiply the coefficients of x and y. In this example, we have 5 times 7, which equals 35. 35 seems to be appropriate for this problem. Note that if this number is too small or too large, you can always multiply or divide it by an appropriate value. Next, we find the points to draw the objective function line. When x equals 0, y equals 5, and when y equals 0, x equals 7. So the objective function line is this blue dotted line here. Recall that this is a minimization problem. So to use this line to determine the best extreme point, we slowly move it down towards the origin parallel to itself. If this were a maximization problem, we will move the line upwards away from the origin. The last extreme point the line touches before leaving the feasible region is the optimal solution point. So let's slowly move the objective function line parallel to itself. You can see here that it passes A and C, so it is obvious that point B is the optimal solution point. We now need to solve the two lines that intersect at point B simultaneously to determine the coordinates at that point. Here are the equations. Let's use the substitution method. From C1, we can write x in terms of y to give x equals 6 minus 3y. We can then substitute that expression into C2, and that simplifies to 30 minus 15y plus 2y equals 10, which gives negative 13 equals negative 20, and that gives y equals 1.54. Substituting that y value in the x equation, we have x equals 6 minus 3 times 1.54. That is, x equals 1.38. So the coordinates at point B are x equals 1.38 and y equals 1.54. Let's now plug the points into the objective function. We have 5 times 1.38 plus 7 times 1.54, which gives 17.7. So the optimal solution occurs at point B, and the corresponding minimum value of the objective function is 17.7. See you in the next video, and thanks for watching.
Moving on to the next presentation, it is about the linear programming graphical solution with negative coefficients. This video shows how to graphically solve a maximization linear programming model that has, first, constraints with negative coefficients, second, functional plotting points.
Welcome. In this tutorial, we will solve this maximization problem using graphical method. Let's label the constraints C1 to C4 for reference purposes. Let's start by setting up tables to find the points. The line equation for constraint 1 is 7x minus y equals 3. So when x equals 0, y equals negative 3. And when y equals 0, x equals 0.43. These 2 points are not that useful to us because the first has a negative, which will take us far away from the feasible region and make the graph very small. The other has a fractional value that cannot be easily located on the graph. So let's try finding more points. To make it easy to find useful points, it is better to rewrite the equation in terms of one variable. In this case, we write it in terms of y. That is, y equals 7x minus 3. We can now use trial and error to find better points. For example, when x equals 0.5, y also equals 0.5. And when x equals 1, y equals 4. For constraint 2, we have the line negative 3x plus 6y equals 10. When x equals 0, y equals 1.67. And when y equals 0, x equals negative 3.33. Again, let's try more points. Rewriting the equation, we have 6y equals 10 plus 3x. So that y equals 10 plus 3x divided by 6. When x equals 1, y equals 2.17, and when x equals 2, y equals 2.67. So it is hard to find whole number points for this line. For constraint 3, we have the line 3x plus 4y equals 9. When x equals 0, y equals 2.25, and when y equals 0, x equals 3. Let's try one more point. When x equals 1, y equals 1.5. And finally, for constraint 4, we have the line 3x plus 3y equals 3. So when x equals 0, y equals 1, and when y equals 0, x equals 1. And that should do it for that constraint. In drawing the line for the first constraint, we can just plot the last 2 points, 0.5, and 1, 4, and then the constraint line. For the second constraint, we can use the first point and the last 2, and that's the line. For the third constraint, we can use 3, 0, and 1, 1.5, and that's the line. For the fourth constraint, we have 0, 1, and 1, 0, and that's the line. Now, the first 3 constraints are less than constraints and are satisfied in the direction of the origin. The last constraint is a greater than constraint satisfied in this direction away from the origin. The directions of the arrows show that the feasible region is this shaded area in blue. To determine which of the extreme points of this feasible region is optimal, let's use the objective function line method. The objective function is to maximize negative 3x plus 12y. We begin by setting the objective function to any number of our choice. Normally, I would just multiply 3 by 12, but that would give us 36, which would give us a line too far away from the feasible region. But since 12 is a multiple of 3, it will be a better choice in this case. So let's set the objective function equal to 12. Next, we find points to draw the objective function line. When x equals 0, y equals 1, and when y equals 0, x equals negative 4. Because of this negative 4, let's just obtain one more point. When x equals 2, y equals 1.5. So using these 2 points, the objective function line is this dotted line here. Since this is a maximization problem, we slowly move the objective function line upwards away from the origin parallel to itself to obtain the optimal solution point. Now, moving the objective function line shows that the optimal solution occurs here at the line intersection of constraint 2 and 3. Let us now solve these 2 lines simultaneously to determine the coordinates at that point. Here are the equations. Since the coefficients of x in the 2 equations are negative 3 and positive 3 respectively, we can simply add the 2 equations to eliminate x. So negative 3x cancels 3x. 6y plus 4y gives 10y, and 10 plus 9 gives 19. On dividing both sides by 10, we have y equals 1.9. Substituting that value of y in C3, we have 3x plus 4 times 1.9 equals 9. That is, 3x equals 1.4 and x equals 0.47. So the optimal solution is x equals 0.47 and y equals 1.9. Plugging that point into the objective function, we have negative 3 times 0.47 plus 12 times 1.9, which gives 21.4. So the optimal solution is x equals 0.47 and y equals 1.9. And the corresponding maximum value of the objective function is 21.4. See you in the next video, and thanks for watching.
I hope you have learned something about the topic linear programming, the graphical methods. Thank you for watching and thank you for listening. Once again, this is Friday of Seeing. See you next meeting.